Hi, I'm Stephen Cahill and I'm a physics teacher. A few weeks ago, Alan Becker put out an animation versus physics video. And since then, people have been asking me about it and saying, oh, what's your opinion on this? And can you explain how accurate this is? So today we're going to review that video and explain some of what happens, as well as calling out any mistakes that we notice. Now, I realize that this is an animation and not a simulation, and there are going to be some inaccuracies for the sake of plot. So we're going to give a bit of grace in that, but I do want to call out inaccuracies without necessarily being too pedantic, including some of the background details. Now, my level of expertise is in the topics of physics which are taught in high school, but I can comment on some of the other things as well. Now, if you haven't watched the original video yet, go do that now. The link is in the description. I'm also going to assume that you have a bit of physics knowledge already, and that you've at least heard of many of the things in the beginning parts of the video, even if you aren't familiar with all the details. So with that being said, let's go ahead and get to it. Now, I said that we weren't going to get too pedantic, but I'm going to start off with a nitpick. Typically, when we're talking about velocity, we would want to introduce the concept of displacement first, because velocity is a change in displacement over a change in time. Now, he's going to get a pass on this because he's about to introduce displacement, but if we're looking at distance and time, then that is defined as speed. Now right here, this is looking at average velocity. That's what that little bar above the V means. Now here, I love how when we're showing acceleration, we're showing how it is one velocity vector and it's another velocity vector that's being added to it. So we're showing addition of vectors as well as just numbers getting bigger. If the force that you exert on an object and its displacement are in the same direction, then work is going to be force times displacement. But technically, the full equation is force times displacement times the cosine of the angle between them. So if they're going in opposite directions, then it's actually negative force times displacement. So when it's showing him lift up the ball and the work arrow is going upwards, that's great. When he's lowering it, the arrow does go downwards, showing that there is negative work, but it kind of also just changes to power. And I would have loved if they would have made that a little bit clearer, because I think that the idea of negative work is very much a thing that people would have been, it would have been nice to have shown. And now we come to the first actual mistake of the animation. Now, we see that when the ball is bouncing on the ground, it has two vectors. There's a vertical and a horizontal vector. The vertical vector is force times the cosine of the angle, and the horizontal one is the force times the sine of the angle. Now, everything that is wrong. First of all, we see that when the ball is bouncing and it's going up and down, the vertical vector is changing and the horizontal vector is not. Now, that means that these are not really force vectors, these are actually velocity vectors. It's showing the horizontal and vertical components of velocity of the ball. So, strike one. Strike two is that the angle that is shown is the launch angle, or the angle that the ball is leaving the ground. Now, when you are breaking down a vector into components, with an angle that is between the launch angle and the horizontal, the vertical component is going to be multiplied times the sine of that angle, and the horizontal component is times the cosine of that angle. So not only is it not a force vector, but he also switched the components of the cosine and the sine. So this is not good. Now, if those were force vectors, then what you would expect to see, the horizontal force vector would be very high when he throws it, but then after that, there would be no horizontal force. The vertical force would also have an initial spike when he throws it, but then while the ball is in the air, you'd only have a constant force of gravity downwards. But then when it hits the ground, you'd see a massive spike upwards. And then when it's in the air again, then you just see a constant force of gravity downwards that doesn't change depending on the height. So all in all, those vectors are just inaccurate. Now, what he does do well here is showing that the trajectory of a projectile is a parabola. So that is good. Okay, this is going to be one of the sections that has a lot of commentary. So we introduce friction, and we see that little cursive U-looking thing, which is the Greek letter mu. That is the coefficient of friction. It doesn't have any units, that's correct. And we see that when he skids on the surface before he gets to the ice, it is 0.5. Now, when he goes out onto the ice, we see that his coefficient of friction becomes 0.1. Now, coefficient of friction is between two materials. So between him and the ice is 0.1. Now, that is actually a little bit high for ice, but it's kind of within an acceptable range, so that's fine. But it is much lower, but it is not frictionless. Now, most objects have a coefficient of friction that is different depending on whether something is static or whether it is moving along that surface. So if something is just staying in place, it will usually have a higher coefficient of friction than it does if it is actually moving across the object. Now, this does not have a higher static coefficient of friction, but that's okay. Now, what's not okay are these arrows. I am really not sure what they are all supposed to represent because they kind of change throughout. So I think that the white arrow is supposed to be the force that his leg is exerting on the ground in a horizontal direction. And it's showing that, okay, this leg, which is a little bit tilted that way, is exerting a force that way, and it's got a frictional force that's the black arrow going that way. Now, that's fine right here, but that changes as the scene plays out. Now, we see here that he's not moving. And this could be one of those cases where we're just ignoring physics for the sake of plot. And I think that that is what is best described as. But a lot of people have tried to justify this and say that this is accurate. Now, if this is frictionless, then sure. But we did see that it had friction, and we still see that it says mu equals 0.1. So it's still implying that he has a coefficient of friction. So this is not an accurate scene. What should happen if there is friction would be that his feet are, propelling him forward. And that would be with an acceleration that is equal to mu times the acceleration of gravity. And that's a fairly simple calculation if you know how to do force body diagrams and how net force works. But it would be very noticeable even with a very low acceleration of gravity, even with the low acceleration, or even with the low coefficient of friction of ice. A lot of people have tried to say that this is not an inaccuracy. It is. It is 100% an inaccuracy. I think I'm forgiving of this because it happens for the sake of plot, and it is harder to show some of the future concepts with friction. So I'm okay with the fact that this is turning into frictionless ice, but it is kind of flip-flopping between frictionless and frictional. And we'll see later on that, he's not slowing down when he's sliding. So again, that's just an example of this ice is frictionless at times, frictional sometimes. Linear momentum is a vector quantity. It is a cross product of momentum and the radius. And I figure that that's a fairly small inaccuracy, but they probably would care about this. It's a little attention to detail that I think that they could have done a better job with. Also, the P that they show here is a capital P, and that's usually reserved for power. Momentum is usually lowercase p. Technically, this is precession because you are changing the direction of the axis of rotation. Most people, when they think of precession, usually think of gyroscopic precession, which is where you are applying a torque to cause that to change, and you feel a torque at a right angle to that, which you cannot observe when you just have an object on a rope, because you can't apply torque on a rope like that. So technically correct, and you do have him spinning the other direction, which is not a result of precession. That would be a result of conservation of linear momentum, although it's kind of presented awkwardly, and yeah. Okay, this is one of the other sections that has a bunch of people talking and a lot of misinformation and a lot of people talking about how this is a mistake or this isn't a mistake. So it depends on whether you're still looking at the ice as frictional or not. Actually, I take it back. It's a mistake either way, but I'll say it's a mistake kind of for the sake of plot, so I'm a bit forgiving of it. But if the ice does have friction, he should be able to just walk on the ice. I'll go back to that again. He should be able to walk on the ice if it does have friction, but he's doing this because the ice doesn't have friction. That's why he's not able to walk. Now, because the ice doesn't have friction, when he is swinging the ball around, he should actually be shifting around along with the ball. So when the ball goes this way, he's going this way. When the ball goes this way, he's going this way. So we see a bit of a back and forth as the two are basically orbiting each other. Even in celestial bodies, when you have the sun and a planet, and you have the planet rotating around the sun is not stationary. The sun is actually moving around in a little orbit as it is being drawn towards the planet. Same sort of idea for this. If you want to see examples of an Olympic hammer throw event, you see someone who is swinging around a very heavy object, and their body is not staying in the same place. Their body is acting a bit as a counterweight, and so their body is moving in response as well. Now here, we do not see his body moving, so this is kind of like the ice is frictional here. After he does this the first time, he slides to a stop. So the ice is actually frictional here. This can actually work. but in a more limited capacity than what's shown. So let's kind of go through how this would work. This is really best viewed as a conservation of momentum problem. Basically, when one object goes forward, the other one has to go backwards, or something else has to go backwards. So when the ball is tugging him forward, the ball's forward momentum is coming to a stop. So the ball receives a change in momentum backwards, and he receives a change in momentum forwards. So he's being tugged forward. That part is pretty well agreed by everyone. Now, the issue is, how does the ball get moving in the first place? Now, if you were to take a ball on a rope and you were to whirl it around and you were standing on a normal surface, then the momentum that you give the ball would be equal to the momentum of you and the earth being pushed backwards. And the reason why it's you and the earth is because you and the earth are stationary compared to each other. The force that is pushing you back is not enough to overcome the force of static friction between you and the planet. So basically, you and the planet are being treated as one big mass when you are moving this ball forward. But then once the ball reaches the end and it yanks you forward, that's enough to overcome that static force of friction. So you are being moved compared to the planet. Now, where this falls really short is when he continues to do this, because remember that this kind of relies on you being stationary. Now, once you're already moving, any force backwards or forwards, it's all basically going to be canceled out. So you can do this in short bursts to move yourself forward, come to a stop, move yourself forward, come to a stop, move yourself forward, come to a stop. It will not work if you are already moving. That is another place where this falls short. And again, I don't really have too much of a problem with this because I feel like this is done for entertainment and it is an inaccuracy, but I'm okay with this. But there's a lot of people who do think that this is something that is feasible when it's not. And if people need an example of how this ice is frictionless, then here's another example. He's moving forward and his velocity is not decreasing. One thing that is a little weird is that when the ball is falling, there's a force vector of 600 newtons. I'm assuming that that's the force of gravity. And we see a few seconds later that the ball's mass is 200 kilograms. This means that the acceleration of gravity is 3 meters per second squared. Earth's is about 9.8 meters per second squared. So this is about a third of Earth's. It's kind of comparable to the acceleration of gravity on Mars. So a little detail that I don't know if this is a mistake or if it's just something that they threw in or if it's actually what they used in their simulations, but there's a little detail. This collision is done really well. We see that momentum is conserved, so he is moving forward with an amount of momentum, and then the ball is stationary. After the collision, he is stationary, and the ball has all of the momentum, and that is accurate. This is also an inelastic collision because if we look at the amount of energy that is being transferred, we do see that some energy, some kinetic energy specifically, is lost during the collision. So this is an inelastic collision, and the vast majority of collisions in the world are inelastic. There's usually some sort of energy that is lost to heat or deformation of an object. So this is good. Now, I think that most people who are familiar with energy kind of saw where this is going when they saw that both sides of that valley were at the same height. Uh, and this is a great demonstration of kinetic and potential energy being transferred into one another. But there is a bit of nuance here that may be lost if this is frictional ice. So we're going back to that idea again. So if this surface does have friction that the ball is experiencing, then the ball is not just sliding along and then just kind of sliding down, but it's sliding and it is also rotating. So the kinetic energy that the ball receives is not just translational kinetic energy, but it's rotational kinetic energy as well. So you'd have this potential energy being translated into or converted into kind of both kinds of kinetic energy as this is happening. Now, all of that is if the ice does actually have friction. I think that for demonstrating this concept, it's actually better if it does assume that this ice is frictionless. It just makes everything much cleaner. Trying to demonstrate transfers of energy when you do have energy that's being lost due to friction is kind of messy. So I like it when there isn't friction in this case. It just makes things cleaner. When he shoves himself forward, the ball should roll backwards. This is according to Newton's third law of equal and opposite reactions. And the fact that there's friction, there is friction here because we see him come to a stop. But the fact that there's friction doesn't prevent the ball from moving, because the ball is not just sliding along the surface, but it would be rolling instead. So whether there's friction here or not, the ball should move. I haven't done any calculations on this, so let me know if I'm wrong in the comments, but I think there's actually a possibility that the ball crushes him during this time because it starts with greater potential energy. So that would be interesting, although I'm glad that it didn't happen. Torque is the cross product between the radius and the force applied in that point. And I feel like if they're going to be putting that equation there, then they really should make it a cross product. That's a small detail that's really easy to get right. And I feel like it's actually hard to get wrong. So I'm not sure why they missed that, but another inaccuracy. That was a wonderful demonstration of conservation of angular momentum. It was fantastic. The rope kind of changed lengths, I think, but it wouldn't really work in a real world setting to launch someone into space. But hey, that's plot. I'm okay with that. This is great. We see that he's gone up into orbit and his acceleration of gravity is now 0. This is not accurate because when objects are in orbit, they're still accelerating towards the planet. It's just that they have a sideways velocity that allows them to orbit instead of just falling straight back down to the planet. So the fact that he's gone up and is no longer feeling any gravity is not accurate. Okay, so one minor note, the thrust is not directed at the center of mass of the man and the rocket, so it would eventually end up spinning the rocket and kind of causing it to go around in a circle. We'll ignore that because it would look stupid for him to just be on the front of the rocket. Now that equation for thrust, the force of thrust, that is an accurate equation. And people might see mass time velocity and they might think that that is derived from Newton's second law, F equals ma. But it's more accurate to say that it comes more directly from change in momentum over change in time. So that is why you have a change in mass when there's mass leaving the rocket. We've gone through a lot, and we still haven't even made it to the 5-minute mark of the video. We will speed things up along, I promise. So here we get a glimpse of the Lorentz factor and beta, and these things are involved in relativity. So basically anything that involves kind of time dilation or space dilation, you're going to be using the Lorentz factor. And so this is accurate, and it is really only noticeable when you are a very appreciable fraction of the speed of light. I love this shot because when he's shining his light on his face, it is actually shining through his face to land on that celestial object behind him. So that's a neat nod to the fact that he is actually a stick figure. So that's really nifty. Now, as far as inaccuracies go, the light would have to be insanely bright to actually illuminate a celestial body like that. The light also doesn't travel instantaneously, so it might not show up as quickly as it does in this animation. But both of those I'm willing to forgive because it's telling a story. Now here where he is putting his hand in the light beam and we see wavefront, the wavefronts are actually those white lines that are traveling away from the flashlight. And it's more of a representation of what the wave is doing than the actual reality of how light travels. But a more accurate term to use for, well, the accurate term to use for light bending around an object is diffraction. So that would have been something that I would have preferred to see. I think that's something that they didn't do their research on, but yeah. Now, we see in this section that they got the greater than and less than signs confused, which is kind of embarrassing. Ultraviolet light is less than 400 nanometers, and infrared is greater than whatever value they showed. Okay, so that is the equation for how velocity changes in a gravity slingshot. So that is an accurate equation. I don't think that the motion of the planets really matches what it showed us in the animation before, but it does show us that vector of the planet's motion, which it does work. It is accurate as far as the numbers go. A number of commentators have talked about how there's no air in space and you wouldn't be able to wave your hat and that wouldn't change anything. He's riding a rocket in space with a cowboy hat. He's, whipping the rocket with his hat. He's spurring it on. This is not something that is meant to be realistic. This is plot. This is funny. Let's just accept that. Those three vectors that you see there, force, current, and induction, those are often referred to as the right-hand rule for electromagnetism. I don't feel like it's being used in the correct context here. Most of the time when I see it, it's being used to refer to current flowing through wires and the magnetic field that they produce. So let me know in the comments if I'm wrong, but I don't think that this is really used in the correct way. And also, even if it were, I think that induction is supposed to be the one that's lining up with the magnetic field. So those are pointed in the wrong direction anyway. So yeah, no. So what he's doing is he's aligning the magnetic domains, and this is something that you can do yourself. Just grab a steel nail and a magnet and just move the magnet along the nail in the same direction, and you will basically create a magnet out of the nail. I have no idea what the creators think a solenoid is, but that ain't it. First of all, it doesn't have to be magnetic on its own. The magnetic field comes from the current that's flowing through it, which is problem number 2. The ends of that are not connected to anything so you can't have a current flowing through that. In order to power it, you need to hook it up to a generator or wall outlet or something. Not just put a magnet on top of it. So this is not a solenoid. This does not work. This scene has raised a lot of controversy and discussion. Some people say that it does work, some people say that it doesn't work, so let's go ahead and go through it. Now we're going to keep things simple, North and South Pole. So when a rocket has a North Pole pointing that way, and it is approaching a magnet with its south pole close to the North Pole, then the rocket is going to speed up. And pretty much everyone is in agreement on this fact. But once the rocket passes through the magnet, now its south pole is close to the magnet's north pole. And so these are going to be attracted to each other. But it's headed away, so that means that because of the attraction, it's going to slow down. Now, some people have said, well, it's passing through so quickly, so the point where it's strongest is, doesn't matter. And well, it's the exact same thing that happens on the other side. The signs are just flipped. Whether it's being attracted or repelled, the forces are the same overall. So this will not work. There is one possibility that people have brought up that would work that was not shown in the animation. When the rocket comes close to the magnet and it passes through, the magnet could switch polarity. And then when the rocket passes through, now the south poles are closest to each other. And so now the rocket is going to be propelled away from the magnet. And that will work, but it was not shown in the animation. With a beta of 0.8, your Lorentz factor is going to be 1.667 repeating, so you will have a very noticeable time dilation, although it's not going to be mega different and completely crazy yet. Now, this next part is a bit space heavy, and this is not really my area of expertise. As far as I can tell, they got everything correct. Some things like the Doppler effect, that is accurate, and I can say, yes, they got that right. Some of the other stuff with the black holes and that stuff, I can look at a diagram and I can say, oh, yeah, seems right. So there are other people who talk about this in more detail, and I encourage, if you want to find someone else who has talked about that more in depth and what black holes actually do, then that is something that I encourage you to seek out. Actually, one thing that I do want to comment on, the image that you see of the black hole where it has, this disk around it, and it looks like it has part of the accretion disk that's kind of going over it, that is actually located behind the black hole. But because the black hole is actually bending the light, it is actually changing the appearance of where that thing appears to be. I think that they discovered this when they were modeling with Interstellar, and they looked and they generated this computer model, and they're like, like that looks weird. And they sent it to their science consultants, and they said, actually, yeah, this makes sense. So that is a neat detail that they also included about what a black hole would kind of look like with its accretion disk. So now we're getting into the realm of subatomic physics. So the first thing that we see is an electron orbital. This is basically the region of probability of where you would expect to find an electron given those particular quantum numbers, 2, 1, and 1. And that is indeed the shape for those quantum numbers for a hydrogen atom. We would only expect a hydrogen atom to have one electron, but it could have that energy level. That's not a problem. So yeah, this is fine. Now, because this is a hydrogen atom, we don't have a neutron, or we wouldn't expect to see one anyway. So that's accurate. Now, diving into the proton, we see that it is made up of 3 quarks. We have 2 up quarks, that's their flavor, and then 1 down quark. And we have a red, green, and a blue. And so their colors are balanced. And if you want to go more into that, then I suggest looking at quark theory on Wikipedia or somewhere else. We're not going to be getting too much into that here, but this is accurate. I don't know why they had an anti-quark there. That is not something that you'd expect to find in a proton, so I don't know. This is where my area of expertise comes to an end. I can't really provide any more meaningful commentary on how well they did or what they got right or wrong. It's just been too long since I've studied most of this stuff. So if you're interested in some of it, they do a very good job of labeling all of the terms that they use and the theories they're referring to. So if you're curious, then you can read up on some of those concepts yourself, but this is going to be it for me. Overall, it was a really fun animation. It touched on a lot of different fields and topics within physics. There were some errors and mistakes. Most of them didn't detract from the quality at all. I certainly didn't notice most of them on my first watch through. But there were some minor details that did get through that I really feel like it would have been simple to fix or to get it right in the first place. So I am a bit disappointed that those did make it through. Now, as a physics teacher, would I show this in my physics class? Maybe. I feel like it was made for people who love physics, not for everyone. It's not an instructional tool, so it doesn't really teach anything by itself. But it might be good for inspiration at the end of the year to say, if you pursue physics, then these are some of the topics that you'll be getting into. Or to say, hey, remember some of the things that we went through earlier in the year. Do you remember these things? Here they are in an interesting format. Or maybe during certain units, I could play a certain part of the video or assign that for homework and say, what are some mistakes that you noticed here? So in a way, that is still a good way of using the video. But overall, I had fun watching it and breaking it down. If you made it to the end of the video, thanks for watching. I probably won't make too many videos like this, so you don't have to subscribe, but drop a like if you want to say thanks, and hope you have a good day.